All right, welcome back to Étale cohomology. So last time we proved Serre's Kähler analog of the Riemann hypothesis. So that was a statement about the action of certain endomorphisms of smooth projective varieties on their cohomology. We reviewed the definition of an Étale morphism, and we gave some motivation for what we're going to discuss today, which is the idea of a site, which was a generalization of a topological space, or a generalization at least of certain aspects of a topological space, namely the category of open sets on a topological space. And the goal was to generalize topological spaces to sort of less topological settings, namely categories, and to define sheaves in those settings. So what we did last time is we discussed what you need to define a sheaf, and we decided we need a notion of when a bunch of open sets cover an open set, and we need a notion of intersection of open sets, which we said was going to be something like a fiber product. Okay, so with those two things, let me make the actual definition, which we'll be studying and giving many examples of today, which is the definition of a Grothendieck topology. On a category C. Okay, and given such a thing, namely a category with a Grothendieck topology, we're going to call that a site, or sometimes we'll call that a Grothendieck site. Okay, so what is this? So this is the following data. So it's the data of, for each object of C, a collection of sets of morphisms, so a collection of sets of morphisms x alpha to x, so indexed by some set alpha. So here the alpha index the morphisms in this set, and then for each x we have many such sets. Okay, so these are called covering families. And this data of a bunch of covering families has to satisfy a bunch of axioms, and those axioms are motivated by like what it means for a bunch of open sets to cover another open set. So the Zeroth Axiom is just that kind of intersections exist. So you're supposed to think that this is meaning that intersections exist. And this is the statement that if x alpha to x appears in a covering family, and y to x is arbitrary, then the fiber product of x alpha with y over x, so you're supposed to think that's like the intersection of two things, or the intersection of y with an open of x alpha, has to exist. Okay, the next axiom is that if you intersect with a cover, gives a cover of the intersection. So what's the situation? So here's the rigorous statement of that. So if x alpha to x is a covering family, so you're supposed to think of this as saying the open sets x alpha cover x. And so if you have a covering family and an arbitrary morphism y to x, so then you can pull back the covering family. So then y times x alpha over x to y, so these are like the pullbacks of these morphisms, is a covering family. So in the situation where C was the category of open sets on a topological space with morphisms given by inclusion, the existence of this morphism y to x is saying that y is an open subset of x, And then this axiom says that if you take an open cover of X and intersect it with an open subset of X, you get an open cover of that subset. Okay, so the next axiom says that a composition of coverings is a covering. So how do we phrase that categorically? So what we say is that if X alpha to X, and then also X alpha beta to X alpha are covering families. So if you're here, let me explain what I mean by this. So here, I mean, we have a cover of X, X alpha to X. So here, that's a bunch of things mapping to X, which we're calling cover. And then for each of those X alpha, we have a cover of those X alpha. So if we have this data, then you can compose. You can go from X alpha beta to X alpha to X. So then the sort of union of all these compositions, so if you go X alpha beta to X alpha to X, in all possible ways, like all possible ways of combining these things. So here for each map X alpha beta to X alpha, you can compose it with a map from X alpha to X. So then this is supposed to be a cover family. Okay, so what is this saying in the setting of topological spaces? It's that if you have a cover of an open set by subsets, and then a cover of each of those subsets, well, that means you've covered the whole set. Okay, and then finally, there's the statement that isos are covers. So if X to Y is an isomorphism, then this sort of singleton covering family is a covering family. Okay, and that's just saying a set covers itself. All right, so are there any questions about that? So this is the definition. This is somehow the idea that this is all one needs to define a sheaf, and I'll explain how one uses this to define a sheaf in a second. Is sort of one of the big insights at the beginning of the theory of Étale homology. So maybe let me pause for 7 seconds, and y'all can tell me if you have any questions about this admittedly very long definition.
Are there any condition? Is there any condition that sort of gives surjectivity of a cover?
No, actually. So for example, you could take if you have a category with fiber products, you can just take all collections of morphisms to be covering families. So that's like giving a space kind of the discrete topology thing. And that's not a very interesting topology, but it's a perfectly well-defined Grothendieck topology.
But I'm looking at axiom 0, or the definition of a cover. If I just think about the case of a topological space, if I had a proper subset of a bigger set, and I declared the map from the smaller set to the bigger set a cover, is there something that would go wrong with that?
Or I mean, it wouldn't violate the definition. I think yeah. What I would say is that there are situations in real life where maybe there is some underlying topology, but we still define things that don't look like topological covers to be covers. So for example, one thing you might try to do is maybe you have a formal scheme, and you would try to understand covers of the generic fiber, right? The generic fiber isn't something that actually exists for a formal scheme. So that you can write down a category which looks like covers of the generic fiber, and such things need not maybe have good behavior along the sort of closed fiber of your formal scheme. Right. So I think there are actually situations where in real life one might want to declare things that aren't like naively topological covers to be covering families.
Okay.
Yeah. Yeah, I mean, one of the cool things about this is, like, just like a topological space, you can make your own. So you can make your own growth unique topologies if you need to do certain things, and that's something that, like, genuinely people do. Like, they'll invent. You're trying to. Well, we'll see. I mean, that's what growth unique did, but we'll see maybe later some other sort of more exotic growth unique topologies. All right, so let's actually give some examples. So I've already kind of given one, which was, I think, the kind of motivating example. So if X is a topological space, I'm going to define the category C to be the category of opens in X. So the objects are just open subsets of X. And then there's a morphism, there's a unique morphism U to V if U is contained in V. So this is it's the poset category. Okay, and then what are covering families? So we say U alpha to U is a covering family if just, well, the union over alpha of the U alphas is equal to U. Okay, so that's the motivating definition. I mean, I'm not going to check that it satisfies all the axioms, because I sort of, as I described the axioms, I explained why it satisfies them. Are there any questions about this example? All right, so let's do some more examples. So the main example, well, the main examples for the course will be the so-called Étale site and the small Étale site and the big Étale site. So let's do those. So there's X is going to be now a scheme. And then I'm going to define kind of two Étale sites associated to it. So one of them is called the small Étale site, which Milne denotes with a lowercase et. And I'm going to try to always say small Étale site or big Étale site rather than just using the lowercase or uppercase letter, because I think it's a little hard to read sometimes. Okay, so this is going to be the category. So this is the category whose objects are Étale morphisms y to x. So here y is any scheme and f is any Étale morphism from y to x. And then morphisms are morphisms over x, are maps of schemes over x. So meaning we have y1, y2 to x. So these are some Étale morphisms. Let's call them f1 and f2. And then a morphism between these two is a map G like this. Okay, and then what's a covering family? So x alpha to x is a covering family if it's a covering family. So if the union, the images of the F alphas, so here I just mean the set theoretic images at the level of underlying topological spaces, is all of that. Okay, so that's the so-called small Étale site. Are there any questions about that? So this is the site.
I think I have one. Do you assume Z is Étale or does it follow from?
Do I assume that G is Étale was the question?
Yes.
Yeah, G, it follows. So there was this 2 out of 3 property we discussed last time about Étale morphisms, and that implies that G is Étale. That's a really good question. Okay, so let's now define the big Étale site, and I think Milne uses a capital E to distinguish this from the small Étale site. So this is a different category. The underlying category is genuinely different. So this is the category whose objects are all X schemes. So that just means a scheme with a map to X. That map is not required to be Étale anymore. So again, morphisms are going to be maps over X. So the underlying category is just the over category, the category of schemes over X. Okay, and now what are covering families? So now we say U alpha to U, F alpha, is a covering family. If, again, so first of all the F alpha are Étale, and the image, the union of the images of the F alpha is U. Oh, and here I should have, by the way, I shouldn't use X twice here, so this should be U alpha to U. So remember, a covering family is supposed to say what a cover of any subset is. So yeah. Okay, so why is this one small and this one big? Well, it's because this one is a much larger category, right? So here we include only Étale X schemes, and we're looking at covers of those. Here we take all X schemes, and we look at Étale covers of those. So what it means to be a covering family is the same, but there's just way more objects. Are there any questions about that?
I just want to confirm here the image makes sense because, as you mentioned last time, Étale morphisms are also open, right?
That's actually not really necessary. So it's all I'm just using is that if you have a map of schemes, you have an underlying map on topological spaces.
Oh, I see. So here,
the map image of a map of sets.
Okay, so that image there is just the underlying top space image?
Yeah, that's right.
Okay, cool.
Yeah. So in principle, I mean, there are examples of very reasonable growth-unique topologies where your maps aren't open. Although I think all the ones we're going to discuss in this course, I think, will always be in the situation where maps are open, and I think in the situation where covers are honest topological covers. All right. Are there any questions?
Is it going to make much of a difference in terms of a cohomology, which site we consider, the big one or the small one?
Not really. So one difference is that the sheaves on these categories are different. So it's much easier to define a sheaf on the small Étale site. You only have to say what it does for Étale maps to X. On the big Étale site, you would have to define it for every single X scheme. And that's not always something that's so easy to do. But no, from the point of view of computing the cohomology of the sheaves we actually are going to care about, typically it won't matter. Yeah, that's a good question. Okay, let's do some more examples. So suppose X is a complex analytic space. If you don't know what that is, you can just think a manifold, a complex manifold. So then there's the analytic Étale site. So here as a category, so the objects are complex analytic spaces Y mapping to X. So let me call this F, such that locally on Y, F is an analytic isomorphism. So for example, this allows covering spaces of X. Okay, and then again, morphisms are going to be morphisms over X, maps of complex analytic spaces over X. And then I'm going to just write covers are covers. Meaning, again, a collection of maps is a cover if the union of the images is the whole thing. Okay, so maybe let me remark. I mean, I think this category is somehow the motivation for the definition of the Étale topology. This is supposed to be what we're trying to imitate. So for example, if you have an Étale cover of a complex algebraic variety, its analytification is one of these things. And so this site is going to show up when we compare Étale cohomology to singular cohomology later in the course for complex varieties. And so maybe just a remark. We haven't said what it means to be a sheaf yet, but I want to give you an example. I want to make a remark about this topology to show you that growth topologies behave in sometimes unexpected way. So the category of sheaves on the analytic Étale topology of a complex manifold, say, is canonically equivalent to the category of sheaves on just the underlying topological space. Okay, so here these are evidently two different growth topologies. So on the right hand side we have the growth topology which we associated to any topological space in our first example, which was kind of our motivating example. And here's some kind of funkier thing. So what this is saying is that sometimes the category of sheaves on a growth site doesn't actually remember the site. Right? Two different sites can have kind of equivalent categories of sheaves. And this is actually this equivalence will show up crucially when we compare Étale cohomology to singular cohomology. Okay, are there any questions about these examples so far? All right, so let me give you one more example, which will show up fairly importantly. So this is the so-called Fppf topology.
Sorry, actually, I do have a question.
Yeah, go ahead.
It looks like the underlying categories for these two sites are different. Is that wrong? Okay.
Yeah, they are different. So on the right hand side, you just have open subsets of X, and here we have things like including covering spaces.
Okay.
So they're generally quite different. We'll see in a second that there's a notion of a morphism of sites, which actually induces this equivalence of categories. So
cool.
I'm gonna actually proving this equivalence is going to be an exercise. It's once we have the definitions, like so far you can't do this exercise because you don't know what a sheaf is, but once we have the definitions, you'll see that this is very, very natural. Does that answer your question, Arvind?
Yeah, thanks.
So, and let me just say verbally why this exercise is true, and you'll verify it later. Well, suppose you have a cover of X in this category. So in particular, it's a bunch of local analytic isomorphisms. Well, given a local analytic isomorphism, you can just cover it by small subsets, which are actually isomorphisms onto their image, right? That's the definition of a local analytic isomorphism. So those are also known as subsets of X. So what that means is that given any covering of X, you can actually refine it into a covering by things that honestly kind of come from the right hand side, by cover by honest open subsets.
Cool, thanks.
All right, so let me give you one last example, which is the so-called Fppf topology. So this stands for faithfully flat and finite presentation. So you may notice that that faithfully flat and finite presentation is FFFP, not FPPF, and that's because this is a French acronym. It's fidèlement plat et présentation finie. I don't promise that I pronounced that correctly, but anyway, that's where that comes from. The first P is plat, which is French for flat. And so what is this? So again, there's a big and a small site. Let me just define the small site. So X Fppf. So the objects are Fppf morphisms, y to x. So again, this just means faithfully flat and finite presentation. Morphisms are morphisms over x. And then again, covers are covers, meaning that a map is a cover if it's a collection of maps is a cover if it's jointly surjective. The union of all the images is the whole of X, or the whole of U. All right. Are there any questions about this?
Doesn't faithfully flat imply surjectivity?
Yeah, that's correct. So in particular, every object of this category is a cover of X. But if you have a cover of Y, if you have an object Y of this category, then when you have a diagram like this, so Y1 to Y2 to X like this need not be flat. This need not be faithful, right? So this top arrow need not be surjective.
Thanks.
Yeah. So this is still a condition. Yeah. Cool. Are there any questions about that? Okay, and then let me just, this isn't quite an example, I'm just going to give you like a lot of names of other topologies. Like this is something that's a really useful, yeah. And by the way, I mean, this is a perfectly good definition, but you would get an equivalent definition if you just put flat and finite presentation. Here, I mean, that would be an equivalent category. That might also help. Or sorry, it wouldn't be an equivalent category. The category of sheaves would be equivalent. So maybe that would help us. All right. So let me give you a bunch of other examples. So these are just names. So there's something called the Nizhnievich topology, which lives between the Zerisky and the Étale topology. There's an object called the crystalline site, and that's used in defining crystalline cohomology. There's a closely related object called the infinitesimal site. There's a kind of infinite list of other ones, and as you get closer and closer to the present day, they have more and more annoying names. Like there's the CDH topology and the arc topology and so on and so forth. There's the RH topology, and okay, I'm not going to list every combination of 2 or 3 letters that is now a topology, but these are, I mean, there's like many growth unique topologies that people genuinely use. And it's somewhere on the internet you can find a fun bestiary which tells you which ones are finer than which other ones. Okay, so those are a lot of examples of growth unique topologies. I'm about to start telling you. Oh, so Sophie asks, what is the Zerisky topology? That's a great question. So if you have a let me maybe give you that example. So if X is a scheme, then the Zerisky topology, well, let me do the small Zerisky topology. So this is just it's the open subsets of just the underlying topological space of X with the usual growth unique topology with covers as covers. Does that answer your question, Sophia? I'm going to assume it does. Yeah. So this is, I mean, a scheme is a topological space with the Zerisky topology. Yeah. Thank you for asking about that. I should definitely make that explicit. Yeah. So a scheme has an underlying topological space with the Zerisky topology. So we just use the growth unique topology of that topological space. There's also something called the big Zerisky topology. So I'm using a capital Z. So now the category is all X schemes. And we say that U alpha to U, F alpha, is a covering family if the F alpha are Zerisky open embeddings. And the usual thing, the union of the images of the F alpha is equal to U. Okay, so okay, and why is this what people would normally call, I think, the Zerisky topology, like a sheaf on this site we're about to define sheaves, is just going to be the same as a usual sheaf on the underlying topological space or like the underlying scheme. Okay. So for example, quasi-coherent sheaves will give examples of sheaves on the small Zerisky set. All right. So are there any other questions before I move on to defining pre-sheaves and sheaves? All right, so let's define a pre-sheaf. How much time do we have? Okay, I think so maybe I'll define a pre-sheaf and then we'll take a small break and come back with sheaves. So definition of a pre-sheaf. So on category C. So a pre-sheaf, so a D-valued pre-sheaf, where D is some category, is just, it's a contravariant functor. F from C to D. So for example, if D is the category of sets, then you get a set valued pre-sheaf. Okay, so a couple remarks. So the remark is that this makes no reference to the Zerisky topology. So you don't need a Zerisky topology on C. Okay, and just as an example, if X is a topological space, then a D-valued pre-sheaf on X is just the same as a pre-sheaf under this definition on the category of open sets. So why is that? Well, a pre-sheaf associates to each open set some object, and then to each morphism, so each inclusion of open sets, a map on objects going the other way. Are there any questions about that? All right, so now we can define a sheaf. So, okay, so what's the motivation here? So if you have a topological space, a sheaf is a pre-sheaf satisfying some condition, right? The condition is that its sections, so the values of the pre-sheaf are determined by what they are on an open cover, and given values on an open cover which agree on intersections, you can glue. Okay, and there's some funny diagram people write in order to capture both of those things, and what we're going to do is just write that diagram in the setting of a Zerisky topology. So this is a sheaf on a site now. And so let me just remind you, a site was a category with a Zerisky topology. So it has the extra data of some covering families. So what's a sheaf? So a sheaf F is a pre-sheaf such that the following holds, such that F of U, well, F is a contravariant functor. So if we have a bunch of set of objects U alpha mapping to U, we get a map to the product over alpha of the values on U alpha. Okay. And now what we can do is we can look at the intersections of alpha and alpha prime for all pairs of alpha, alpha prime. And so well, let me just write down the diagram and then we'll explain what it means. So U alpha times U alpha prime over U. Okay, so we have this diagram, and the condition is going to be that this is an equalizer diagram. For all covering families. U alpha to U in our site C. Okay, so let's figure out what this means. So first of all, what are these two arrows here? Can anyone tell me?
First and second projections?
Yeah, that's right. So if you have U alpha times U alpha prime, so this maps to U alpha. and U alpha prime, just by the fact that it lives in this diagram, right? So those maps, those first project and second projections, induce maps going the other way when you apply f, because f is a contravariant functor. Okay, so this is, let's call this maybe pi1, and this is pi2. So then this top map is maybe f of all the pi1s that show up, and the bottom one is f of pi2. Okay, so can anyone try to put this, what this equalizer diagram means, like what this being an equalizer diagram means into words? Maybe if f is a set valued sheaf.
If a collection of sections agree on overlaps, then they come from a global section.
Yeah, so that's somehow exactness here. So that says if I have a bunch of sets here, a bunch of objects here, which go to the same thing on intersection, so that means their images under these two maps are the same, then they come from here. So that's part of being an equalizer. That's the gluing condition. So the other part is that this first map is injective, right? So that's saying that a section of f is determined exactly by its values on a cover. Right. So let me actually write that down. So so f of u so let me just say what happens in, so suppose f is valued in sets. So let's write it down what it means to be an equalizer. So by the way, if you haven't seen, if this equalizer notation is not familiar to you, it's saying that this left-hand side f of u is the limit of this diagram in categorical sense. Okay, so what does this mean? So this means one, that f of u to the product over alpha of f of u alpha is injective. So this is saying the values of f on u is determined by its value on u alpha. And two, so given some section, which we can think of as a product of S alpha in the product of these f of u alphas, so this is sections on a cover, such that when we apply the two projections, so when we pull back in the two different ways to the intersection, so we're supposed to think these fiber products are intersections. So if we pull back in the two different ways via these two projections, we get things that equal. So if we agree on intersections, then we can glue. So then we're saying that S alpha comes from f of u. So given some stuff on the cover, which agrees on the intersections, it comes from the union. It comes from the thing being covered. Okay. Are there questions about that? Okay, so I've now told you what a sheaf is and a pre-sheaf. I should now tell you what a morphism of sheaves, pre-sheaves are. So this is the definition of a morphism. And don't worry, we'll get lots of examples.
What if the U alpha are the same but map into U with different maps?
Yeah, so here those maps, so here's F alpha and F alpha prime, they're part of the data. Right, so that means that they're thought of as being they're different, I guess. Right, so covering here this covering family, I've omitted the data, but part of the data is the actual map. Does that answer your question?
Yeah.
Okay, and then Arvind asks why is a section to a sheaf called a section? That's a good question. I mean, so usually, or like often in real life, you sort of think of a sheaf as maybe coming from a vector bundle, and then the sections to the sheaf are literally sections to that vector bundle. But that's not always the case. I mean, that's somehow a picture you're supposed to have in mind. In the topological setting where you have an espace étalé, You can always view a sheaf as the space of sections to some map of topological spaces, but there's not, I mean, there's a sort of formal way of making sense of that kind of thing in this sort of more general setting, but that's like typically, at least in my view, it's not so useful to kind of use that formal way of thinking about sheaves. But yeah, I think the motivation is just to think that given a morphism, the set of sections to that morphism is a sheaf. Or associating to each open U in the base, the sections over U is a sheaf. Okay, so let's define a morphism of sheaves or pre-sheaves. So a morphism F1 to F2. Well, here F1 and F2 are just contravariant functors. If they're sheaves, they satisfy some hypothesis. Morphism is just a natural transformation. So in particular, a morphism of sheaves is the same as a morphism of pre-sheaves. All right, are there any questions about that? All right, maybe let's take a 3-minute break since we're just over halfway through. And then I'll come back by giving you a lot of examples of sheaves and slowly starting to actually prove they are sheaves in this Étale topology. How's everyone doing so far?
Going well.
Cool. Yeah, if you have any questions about what we've done that are more casual, maybe now is a good time to ask. So this is a lot of formalism. I think this is the first time we've really gotten into the weeds so far in this course. So it's okay if you're feeling a little bit overwhelmed by all the categorical stuff.
I have a short question about one of the examples earlier. The site. If, say, X is an algebraic curve, is it true that say the small Étale site is equivalent to the analytic Étale site?
So no, that's not true.
Okay.
Yeah, it's so for example, well, okay, so first of all, equivalence of sites is a subtle notion which I haven't actually defined. I haven't even told you what a morphism of sites is yet.
Yeah.
But at least what you can see is that the underlying category, like there's a sort of natural map one way, right? Like given a curve over the complex numbers, you can associate to it an analytic space, but you can at least see that map is not essentially surjective, right? So for example, if you take a genus 2 curve, its universal cover is the upper half plane. That's an object in the analytic Étale site, but it's not the analytification of any algebraic variety.
Okay. But then is it true for the category of sheaves?
Yeah, so it's not true for the category of sheaves either. That's a good question.
Oh, okay. Thank you.
Yeah, so at least one reasonable notion of an equivalence of, well, not of sites, but of maybe topoi, is that you have some adjoint pair satisfying some conditions, which induces an isomorphism on categories of sheaves, and that doesn't happen in that case. All right, let's get started again, then, unless anyone else has questions they want to or things they want to say. All right. Okay, so let me give you some examples. So these are going to be some examples of sheaves on, let's say, X Étale. Okay, so the main theorem, and I'm starting to think that we're not going to be able to prove it today, or as we fall further and further behind what I planned, but that's fine. I want to, I feel like we're going at a good pace. So the theorem is that any representable functor is a sheaf on X Étale. Okay, and in fact, a stronger thing is true, and that's what we'll prove. So any representable functor is a sheaf on the big Fppf site. So I don't think I defined it. I think I only defined the small Fppf site, but let me say the definition. So the category is all X schemes, and then morphisms or covers are Fppf covers. So meaning a bunch of maps which are flat and which are jointless rejected. All right. And flat and finite presentation is crucial. All right, so are there any questions about this theorem? Can anyone use this to give me some examples of sort of concrete sheaves? Oh, and so Ali asks, is this what descent is? And I wouldn't say this is the entire content of descent, but this is part of the content of descent. And so yeah, we're going to prove what people call Fppf descent for quasi-coherent sheaves and Fppf descent for morphisms, probably later in the thing. So okay, so Arvind suggests mu_n as an example. So okay, so this is the functor represented by the scheme mu_n, which is also known as well, if I'm working in over let me just work over K for some field K. So this is spec K adjoint T mod T to the n minus 1. Right. So how do you evaluate un on some x scheme U? Can anyone tell me what its values are in a kind of concrete way?
It's the nth roots of unity.
Yeah. So it's exactly the sections to OU such that f to the n is equal to 1. Okay, so that's pretty concrete. Can anyone give me some other examples?
Is the global sections functor representable?
Yeah. So it's represented by the scheme A1, right? So a section of, so when you say global section, I assume you mean regular functions, maybe like OX?
Oh yeah.
Yeah. So let's call this the sheaf OX. So this is OX of U is just the global sections. It's just defined to be OU of U. Maybe let me call this OX Étale. This is a sheaf on the Étale site, and I'm telling you what its values are. And this is a sheaf. This is represented by, well, if I have to give you an X scheme, it'll be by A1 of X. All right. Can anyone give me any other examples? So Jose says forgetful functor. Can you say a little bit more about what you mean by that? Yeah, I'm not sure. You must be typing. That's all right. So maybe let me give a couple more examples. So there's the constant sheaf. So the constant sheaf Z mod L to the n Z. So can anyone tell me how to prove this is a sheaf given this theorem, and how to figure out what its values are? So Arvind says it's represented by the constant group scheme, and that's exactly right. So this is represented by just, we take the set, meaning like Z mod L to the n Z times X, viewed as an X scheme. So what I mean by this is just take the disjoint union of L to the n copies of X. Yeah, so that's somehow why I'm multiplying everything by x. So Benjamin asks, for to be a representable functor, does it need to be an x scheme? And the answer, I mean, the way I'm writing things, the answer is yes, but in real life, the answer is no. I mean, but if you just have some random scheme, like over spec k, you can make it an element of x Étale just by multiplying by x. And then a map to that over x will just be the same as a map not over x to your original thing. So somehow that's the proof that if you have a functor which is kind of represented by something that's not an x scheme, then you can make an x scheme that represents the same functor in x Étale. Does that answer your question, Benjamin? Great. Okay, so let me actually say, so we can actually now say what the values of z mod l to the n z on some u are. They're just continuous maps from the topological space underlying u to just the set z mod l to the n z with the discrete topology. Okay, and this is something that should be familiar. Like if you take the constant sheaf on a topological space, it doesn't associate to every open set z mod l to the n z. It associates to an open set z mod l to the n z to the number of components. Components is a reasonable thing. Or if you're in a weird topological space like a profinite set, it'll associate continuous maps like this. So this is some way of saying that you know, this is some way of capturing that we want a sheaf, not just a pre-sheaf, right? Like the thing that associates to every open set u, just the group z mod l to the n z wouldn't be a sheaf. It would just be a pre-sheaf. Okay. Maybe let me give you one more example. So an example is so we can set we can take the sheaf GM of u, and what does this do? It associates you take the global sections of the structure sheaf of u, and you take the units in those, the invertible elements. Okay, and this is represented by, well, what people call this the scheme GM base change to x. So this is, if you'd like, spec, if we're over a field, it's spec k t inverse, or maybe I'll just write the general answer is spec z t inverse times x for spec. Okay, and why does this represent this functor? Well, when you have a map into this thing, t has to go to an invertible function. It's invertible. And that gives you this isomorphism. All right.
So there seems to be this implied general thing where if you have like a group scheme, then when you take the product with the base scheme, you get like a group.
That's correct. Yeah. So that's you've made a very good observation, which is that all of these examples I've given are valued in abelian groups. They're not set valued sheaves, and that's because, as you say, the representing object is always a group scheme. And okay, so let me kind of make some comment about that. So sorry, was the person who asked that question Sarah?
That's right.
Yeah, great. Yeah, so one definition of a group scheme is just that the functor represents to sets factors through groups. And to see that that's the same as a group scheme, you use the unit. So yeah, so that's a really good observation. Great. Okay, so maybe I should give one more example, which is not valued in groups. So there's this functor Pn, which sends a scheme U to U Pn. You could write that functor down. It's like a line bundle on U with a surjective map from OU to the n. Right, that's the functor represented by projective space, and that's also a sheaf. Just because I wrote it down, maybe I wrote it down as being representable. Okay, but that's not an abelian sheaf. Okay, so those are a bunch of sheaves. I still owe you a proof they're sheaves. Even z mod l to the n z, if you tried by hand to prove that it was an Étale or Fppf sheaf, it would not be totally trivial. So we're gonna prove that soon. But before we do that, let me just make a definition, which we can kind of do now. So this is a definition-ish, and I owe you a lot in order to make this definition precise. So this is going to be the definition of Étale cohomology. With coefficients in Z mod L to the NZ. Okay, so first of all, what do I owe you? I owe you 1, a proof that this sheaf we define, Z mod L to the NZ, this constant sheaf represented by just like the set Z mod L to the NZ is a sheaf. So I also owe you a proof that the category of sheaves, let's say on the small Étale site. So if you're a sheaf on the big Étale site, your restriction to the small Étale site is also a sheaf because covers in the small Étale site are also covers in the big Étale site. So let me write on the big Étale site or on the Fppf site. So I need to prove that the category of sheaves on X Étale with values in abelian groups is abelian and with enough injectives, say. Okay, and now once that's done, let me define gamma X is the functor that sends a sheaf F to its values on X. And then the definition is going to be that HI X Étale F, or sorry, let me say Z mod L to the NZ. These are just going to be the right derived functors of the constant sheaf. Okay, so this is Étale cohomology. Okay, so maybe let me make a couple remarks about why this definition is not complete. So first of all, we haven't proved that this sheaf is actually a sheaf. Second of all, the fact that this category of abelian sheaves is abelian is really not obvious. So for example, usually when you prove that the category of abelian sheaves on a topological space has co-kernels, you use sheafification, right? What do? You take the co-kernel of the map of pre-sheaves, that's a pre-sheaf, not a sheaf, and then you sheafify it, right? And we actually don't know how to sheafify a pre-sheaf on a site yet. So the usual proof where you make the espace étalé and take sections to that doesn't make sense for a site. You need a genuinely different argument. So this even just showing that co-kernels exist. So the warning is that even that showing co-kernels exist in the category of sheaves on a site of abelian sheaves. And it's true, it's going to be true on a general site. On a site is non-trivial. Okay, and we're going to do it, but you should try it as an exercise. Great. I mean, it's not an easy exercise. But you should give it a try just to convince yourself that there's something to prove. Okay, and then in fact, what'll be true is that in general, the category of abelian sheaves on a site will be a so-called AB5 abelian category, and then having enough injectives is automatic. So that's something. There's something developed where Grothendieck in his Tohoku paper developed some criteria for when an abelian category has enough injectives, and we're at least going to sketch part of the proof. All right, so that's the course is done. I guess we've defined Étale cohomology. No, okay, so we have 15 minutes left. So let me pause for questions first, and then we'll continue. So I know this is an extremely abstract definition, and it's not even a definition because I owe you a lot. But okay, so Arvin asks, is there an easy way to see that gamma x is left exact? I mean, yes, if you just write down what that means, you'll see that it is. I mean, yeah, we can check that if you want, maybe in office hours or something. But yeah, it's I wouldn't say it's obvious. Like you do have to write something down, but if you do write that thing down, you'll see.
So I have one too. So is there a reason you want to look at the constant sheaf?
Is
Like-
there a reason I want to look at the constant sheaf?
Yes, what does it give us, basically?
Yeah, so this is like taking, so you don't have to look at the constant sheaf. There are plenty of other sheaves you can look at, and we'll define later in the course like local systems, and you can take the cohomology of those too. But this is, I mean, I think the motivation for this definition is that if you have a nice topological space, like a manifold, and you take the constant sheaf Z, your Z mod L to the n Z, and take its sheaf cohomology, that's the same as taking singular cohomology with the Z or Z mod L to the n Z coefficients.
I see.
So we're trying to imitate that definition.
Okay.
Does that answer your question?
Yes, yes.
Okay, great. Yeah, I mean, this is, I don't think, like, I think this is a very non-obvious definition and it's very abstract. So you know, if it feels weird to you, like, that's okay. Like it took growth to come up with this. All right. Cool. So maybe let me make one more, give one more example to show you that kind of the properties of these sheaves are not so obvious and really kind of depend on the site you're working at. So let's consider the map GM to GM, where Z goes to Z to the N. Sorry, I think I'm using T for the coordinate on GM. So T goes to T to the N. And here, suppose N is invertible on the base. So maybe we're working over a field of characteristic prime to N. So this gives us a map of sheaves, right? So this gives a map. We have a map of sheaves, which we can look in two different settings. So first we can look at the Zerisky topology. So this is just usual sheaves on the underlying topological space of a scheme, and so we get you know, O cross is the sheaf represented by this. So units in O maps to O cross, and F goes to F to the N is the map. Okay, and then we can also look at this map in the Étale topology. Maybe I'll call this O cross Étale. So it's a sheaf on a different site, the small Étale site. Okay, and my claim is that this map is in general not an epimorphism on the Zerisky site, but it is on the Étale site. Okay, can anyone explain one of these two claims to me? So for example, can anyone explain why this is not an epimorphism on the Zerisky site in general? Oh, so Benjamin asks if gamma is adjoint to forming constant sheaves. The pullback. So the answer is yes, but we haven't yet defined push forward and pull back. So we'll do that. We'll do that probably next time. Yeah, and there will be a good notion of derived push forwards for arbitrary maps of schemes, not just global sections, and so on. All right. So can anyone help me prove this claim? So maybe the easiest thing to do is to show it's not an epimorphism in general. Yeah. So Arvin says it's not an epimorphism on the Zerisky site because you can't make something an nth power after localizing. So yeah. So let me give you kind of an example of that. So let's prove first that it's not an epi as a usual map of sheaves like on the Zerisky site. So it suffices just to give one example, right? So let's just take x to be spec r, real numbers, and n equals 2, and you'll see that this will work in general. So then, well, this is just a point, right? So sheaf is just determined by its values. So then we're just asking if is r cross to r cross, you know, t maps to t squared surjective. Okay, and the answer is famously no. Right. So the image of this map is just the positive numbers. Okay. So what about so it is surjective on X Étale if, again, n is invertible on X. So can anyone help me with this? So what do we want to show? So let's just pretend we're working with usual topological spaces. So what you would want to show is that given any section to the sheaf on some open, you can refine it. So Arvin says we should pass to the open cover spec C to spec R. So that's right in the spec R case. So let's try to do it in general. So what we want to do is, suppose we have a section on some open, we want to pass to an nth to some Étale cover, so that section has an nth root. So given f in GM of U, we want an Étale cover of U such that f obtains an nth root on that cover. So someone suggests just adjoin an nth root. Yeah, so that's a great idea. So let's do it. So here's how I would do it. So here we have a map from U to GM. That's what an invertible function is, right? And then we have this map GM to GM, some Z to Z to the N. So this is Étale because and it's invertible. So that was an exercise from last time. So let's just form the fiber product. Okay, so this is Étale because Étale morphisms are preserved by base change. And then the claim, which you should verify, is that f has an nth root upstairs. Okay, and as Benjamin suggested, there's a more concrete way of writing this. We can just take A1U, so that's spec of the relative spec of OX adjoin T, and then take the subscheme of that cut out by Z to the N minus F. Maybe let me call it Z is the new variable on A1, and I'll take the vanishing locus of Z to the N minus F. Okay, so this is going to be an Étale cover of U. So this is, again, an Étale cover of U. It's actually the same one. And Z is now an nth root. Okay. So that's the proof, and you should convince yourself that this implies. So exercise is check the details. So check that this argument does in fact imply that this map of sheaves is an epimorphism in the category of sheaves. Okay, cool. Okay, maybe one more remark. So here we used that n is invertible in the base to get that this map was this map here over here was Étale. So the remark is that this map of sheaves, GM to GM. So in the Étale topology, if n is not invertible, this thing in general will not be an epimorphism. So but this will always be an epimorphism in the flat topology. Sorry, sheaves on except Ppf. Cool. Are there any questions about that? And the reason why is just that this map is flat. So if you, and finitely presented. So if you just replace the word flat here with Étale here with flat, you'll get a proof. All right, cool. Oh, we only have 4 more minutes. So are there any questions? All right, so if not, let me just make one more definition, and then we'll discuss it a little bit. So I want to tell you what a morphism of sites is, or a continuous map of sites. So suppose T1 and T2 are sites. So remember that means categories with covering families satisfying some axioms. So a continuous map F from T1 to T2 is, and this is weird, it's a functor from T2 to T1, which preserves fiber products. And sends covering families to covering families. Okay, and the sort of canonical example, so note that the functor goes the opposite way as the map, right? So the canonical example is that given x to y, a continuous map of spaces, we get a functor from opens on y to opens on x, which sends an open set u to its preimage. Okay, and by continuity of f, that's an open set. Okay, and then the exercise is check that this is continuous, a continuous map of sites. Great. Okay, so we're out of time. So next time I'll give you a bunch of examples, and then we'll talk about deciding. Okay, so Benjamin asks, can I repeat what I said about GM being GM being an epi in the not being an epi in the Étale topology, but in the flat topology? Yeah, so that's right. So what we showed here is that if n is not invertible on if n is invertible on x, then this map is a epimorphism in the Étale topology. So if it's not invertible, so for example, if n is the characteristic or is divisible by the characteristic, then this in general won't be an epimorphism. So that's not totally obvious. That's something you should try to prove. In the Étale topology, it won't be an epimorphism, but in the Fppf topology, it will be. And here, this proof I gave, in the Étale topology, it just works verbatim in the flat topology if you just replace Étale with flat and a finite with faithfully flat of finite presentation here. So that's also something that's preserved by base change. So we get some cover of U, which is Fppf, where your function f obtains an M3. Does that answer your question, Benjamin? Great. All right. So we have 1 more minute. So any final questions? So maybe one more remark is that I posted info about office hours on the webpage now, which is on my website. If you just go to daniellitt.com, you can click on Étale cohomology and you'll see it. And the plan is that to have office hours, I think at 10 a.m. on Mondays. So starting this coming Monday. And the Zoom link is a little bit different. So that's on the webpage, and the password, which is the order of the symmetric group on 4 letters, is the same. That's for this Zoom link. All right, thank you all for coming. I'm gonna stop recording now. And